I think I just might get a bit distracted here. Hey everybody, this is John. And I would like to start off with a little challenge. So imagine I have a language L0, and in this language I implement an interpreter for another language L1. And then in this language L1 I implement another interpreter for a language L2. And I continue this process for a while until I have n languages and n interpreters. And I would like to turn this tower or stack of interpreters into a compiler. And moreover, I would like this compiler to operate in just a single pass and be optimal for some value of removing all the introduced interpretive overhead. Okay? And you might say, well, that's kind of an artificial thing, right? Why would anybody care about this? Then, well, these situations actually arise in practice, right? So here's an x86 CPU being emulated in JavaScript, running in a web browser on some other platform, right? And you might think about, okay, well, inside this emulated machine, I can start other software like a Python VM, for example, right? And then you have something that looks like this. So you have Python code, some bytecode language that's running on x86, which is running on a JavaScript VM, and potentially that's running on your phone. So you have an ARM CPU that is actually executing all the instructions. Right? So wouldn't it be nice if we could translate sort of from this stack of nested interpreters, we could derive a compiler from Python to ARM ISA? So in our paper, that's not quite what we did, right? So after all, we're at POPL, so we're not dealing with all these pesky real-world things. So we're doing something that is more principled, right? So we're starting with variants of the lambda calculus as the base language. But actually, I would argue that we're doing something that's even more interesting than sort of the actual real-world languages, right? So we're looking at towers that are conceptually infinite and towers that can also be reflective. And that means that one language in the tower can inspect and potentially modify its own semantics, right? So the interpreter one level up or down, depending from which direction you look. Okay, so this is dynamic languages taking to the extreme. And again, it's not just an isolated academic thing, but this is actually quite useful because you can change the semantics at runtime to introduce logging or instrumentation or profiling, but you can also introduce sandboxing to monitor security policies or completely change the semantics in a certain way, like make modifications to the heap transactional and support rollback or non-determinism control operators. So a whole lot of things you can really do in this setting. And this was explored in the 80s and 90s, so seminal work by Brian Kentwood-Smith, then Dan Friedman, Mitch Wand, and Olivier Donvie, Caroline Malmkier, and more recently Kenichi Asai. So that's a whole series of languages that have been developed in this reflective setting, right? But none of them support compilation, except some recent work by Kenichi Asai on Black, where he has compiled lambdas, but they don't pick up the modified semantics of the language. Okay? So this is our challenge, and well, this is now a question to the audience. Any ideas how we could do this? Any ideas how we could go about this? Just shout ahead. Say again? Partial evaluation, yes. So this is the point where everybody has to scream Futamura projections, right? So since the 70s, we know that interpreters and compilers are related by specialization, right? And just to recap a little bit, the first Futamura projection, what it says is if you have an interpreter, which is a program that takes two arguments, a source program and some input data, and produces a result, then if you have a capability to specialize programs, right? So a partial evaluator, which for historical reasons is quite often called mix, and you apply this partial evaluator to the interpreter with the source program, then you get a specialized interpreter that essentially corresponds to a compiled version of the source program, right? And running the specialized version will hopefully be much faster than just running the interpreter. So that's the idea. The practical realization, of course, is much harder. just because automatic partial evaluation is a really hard problem, right? In particular, the binding time analysis part, figuring out which are the things that really should be specialized away and which things should remain as residual code, okay? So in many settings, sort of the winning strategy is to use a little help from the programmer and let the programmer specify the binding time annotations manually, right? And in that sense, we're explicitly staging the interpreter. And in order to do that, we need a language that supports staging operators, right? But the key realization here is that a staged interpreter really is a compiler. And staging facilities exist in many forms. So there's multi-level calculi, which have staging annotations on each base application or lambdas. Then there's quasi-quotation like in Lisp or MetaML, and there are also type-based approaches that use operator overloading like LMS and Scala. Okay, so how can we make this work, right? So the key idea is that, well, we have interpreters, and we know if we stage an interpreter, then we get a compiler. So let's do this, right? So let's stage all our interpreters. Okay, so now we have a chain of compilers. And that means we can translate code from ln all the way to L0, but it's not quite what we want, right? And in particular, it's not operating in a single pass, but we really have to translate from one language to the next, to the next, to the next, and so on, okay? And moreover, it seems to be very difficult to add reflection to such a setting, right? Because if one language might be able to inspect its own semantics, then how could this work if the translation step has already happened, right? So this appears fundamentally difficult. So the key idea now that we came across is that, well, it's sufficient if we just stage the top-level interpreter. And then all the other interpreters remain basically unchanged. And what that means is that essentially we're interpreting the compiler, right? So the top level becomes a compiler, and all the levels below are just interpreting the instructions of the compiler, right? So we're not changing what the compiler is doing, we're just giving it new meaning in terms of the base language. And with that, we actually get a single pass compiler, right? And we can also support different forms of reflection. And in order to do this, we're using a multi-level lambda calculus as the base language, which we're calling lambda up-down for reasons that will become apparent. Okay, and the key thing here is that if we want to have flexibility in how we design these towers, and we want to write the code for an interpreter only once, then we need a form of staged polymorphism, right? So we need to be able to say, okay, well, I have the interpreter source code, and I want to stage it, or I want to keep it as normal, right? And this is something that kind of falls out automatically with traditional partial evaluation, but appears to be much harder in traditional staging systems, right? So if you think about quasi-quotation, then either you quote something or you don't quote it, right? But you lose the ability of having both from the same code. We did recently some other work based on LMS together with Markus Büschel's group at ETH Zurich, where we actually showed that this kind of stage polymorphism is very helpful for high-performance code generators. So if you're interested in that, then there was a paper at Gypsy 17 which contains all the details about this, right? But in this setting, we're really abstracting over the choice of interpreting versus compiling. So our base language, lambda up-down, it's a variant of the lambda calculus, of course. And the main facility that we have is a lift operator, right? So this is used to take a present stage value like a function and transport it to the next stage, right? So so that it will end up as part of the generated code from the compiler. And with that, since lift is just a normal operator, we can abstract over it and realize stage polymorphism. I'm going to show some examples, right? So here's one very simple example. So we're using some scheme-like syntax as a front end. And this is a little string matcher, right? So think of this as an interpreter that's interpreting a pattern and checking whether that's a prefix of another string, right? So R is the pattern and S is the string we're matching against. And this is straightforward, just a recursive function that does character by character comparisons. So you can see if you're checking whether AB is a prefix of AC, you get false, AB and AB, that's true, and AB is also a prefix of ABC. Okay? So now let's turn this little interpreter into a compiler. And the way we do this is that we're adding lift calls for all the primitive values that the interpreter handles, right? So where previously we were returning true or false, now we're returning lift true or lift false, right? Which means that we're returning a code value that when the generated code is run, will evaluate to true or false, okay? And now what we, on the previous slide, you've seen, well, maybe we're in a setting where we're matching the same pattern repeatedly against many strings. So it pays off to compile this into more efficient code. Right? So what we want to do is we want to get a function start AB that partially applies matches to a pattern string and then gets a compiled function that does the matching in a more efficient way. Right? And we do that by calling matches with the pattern as the first argument, and that gives us back a function, and then we lift that function. Okay, so that's the intuition. And what this code generates is shown here at the bottom of the slide, right? So we're all the dispatch, like the null check on pieces of R, all those things are eliminated, right? So these are executed while we're staging the program, right? And only the operations that touch the actual runtime data, right? So the value of S, only those operations remain in the residual code. And one thing that's key here is that we're maintaining the order of individual expressions, the order of evaluation, by inserting let expressions in certain circumstances, right? So you can see here the call to cutter of S, which has to happen before the recursive call. So this one gets bound to a let automatically in order to maintain the sequence of statements here. Okay, and all the recursion is unfolded, so everything gets inlined, and you can see you really just have a cascade of check the first character, whether it's an A, check the second character if it's a B, and so on. Okay. So in the paper, we have a small step semantics for this lambda up-down calculus, and I just want to give a little idea about some of the rules here. So most of the primitive operations like plus or equality checks or isnum and so on are overloaded, right? So there's a variant that works on normal values, and then there's a variant that works on code values, right? So if I do plus on two integer literals, then I get a literal back that does the summation. And if I do the same thing on code, then I get a plus expression. And this reflect that you can see on the right-hand side, this is really just a marker that says, okay, well, we need to insert a let for this, right? We want to bind this to a new name. And then the lift operator itself. So this one is a bit more complicated, of course, and I'm not going to go through all the details here. But yeah, it basically boils down to that we have to do some magic with evaluation context and make sure that we're inserting lets in the right places, right? And also we can go through an example here, so I'm not going to go through this in detail, but again, you can see if I'm lifting a lambda that just has x plus x times x as the body, then what you get back at the very bottom is a code object which has the lambda bound to a let, and inside the lambda you also have the individual statements bound to let expressions. Okay, and in the paper and in the artifact, we also have a definitional interpreter, which is more like in a big step style and uses mutable state to do the let insertion. Good, so that's our base level, and on top of that, we want to build towers of interpreters, right? So what we have on top of this is a small language that we call pink, right? So just to keep in the tradition of giving color names to reflective languages, and this is a meta-circular interpreter. Right? And we realize stage polymorphism in a way that, yeah, the lift operator, we're not using it directly, but we're abstracting over it just by turning it into a function argument. Right? So In a sense, this is very similar to the string matcher I showed you, only that we're not using lift directly, but we're using maybe lift whenever we create a value that is part of the interpreted language, right? So whenever we have a primitive, then we maybe lift the expression. Whenever we create a user level lambda, then we're also maybe lifting this lambda, right? So this means that from the outside, we can configure this stage polymorphic interpreter either as a normal interpreter or as a compiler. And again, so plus and other primitives are just implemented as the underlying primitives in the base language, and environments are modeled as functions, so none of this is really surprising, right? And here we can configure this function using either the identity function as maybe lift, right? So this gives us an interpreter, and now when we apply this to a quoted expression, then it will do the interpretation, right? So no surprises here. If we call eval on the source code of the factorial function, we can evaluate it with some argument. And we can do double, triple interpretation and so on, right? So this is really just what you would expect from a metacircular setting. So when we want to do compilation, then we configure the evaluator with the actual lift operator, right, wrapped in a lambda. And now what we get back when we apply this to the source code of the factorial function is the actual code of the function, right? So we're compiling a quoted S expression into underlying lambda up-down code, right? Which is then executable sort of as a native facility. And we're not getting any code that is kind of like factorial, but maybe has some overhead, but we're really getting exactly the ANF converted form of the factorial code here, right? And this is, really powerful. And it also means that when we iterate this, right, so when we're interpreting the compiler, then what we get is exactly the same code for factorial, right? So we can iterate this over multiple levels and collapse multiple levels of interpretation here, right? And we still get the same code without any extra slowdown introduced, right? So in some sense, this is a very strong version of Jones optimality that extends over multiple levels of interpretation. Some other things we can do here is we can modify the interpreter, right? So what I showed you is just, well, we can iterate this, but of course the question is, well, what's the point, right? So things get more interesting when we actually modify the interpreter, right? So we can add logging, or we can write an interpreter in CPS, and then what we get back is a modified program, okay? So here are some examples. Like I mentioned, so we can add tracing. So this will actually, in the compiled code, it will insert some log statements, or we can write an interpreter in CPS, and then we get a CPS converted version of the factorial function. Okay, so we scaled this up even further. So we built another language which is called Purple. So this one is very heavily inspired and built on Kenichi Asai's language Black. Here, the reflection capabilities are a little bit different, and essentially what we can do is we can have persistent and side-effecting modifications to the semantics of the current language. And in order to do that, we also, since things are much more fine-grained, we also restrict the language in such a way that we expose an explicit facility for compiling individual lambdas. So again, this is also something that was proposed already in Black, but we extended the implementation to actually capture full semantic modifications. And this is actually built on top of LMS and some of the stage polymorphism facilities that we already had. And so the key facility here is that we have this EM construct. So EM stands for execute at meta level, and this essentially allows you to punch a hole in the current execution context, right? And the expression that is an argument to EM, this will be run at one level above in the reflective tower. And here's just one example. Don't have to go through all the details here, but we can define a counter, and then we can replace the function that defines what it means to evaluate a variable reference. So whenever we encounter a variable that is called n, then we increment this counter. Right? And if we do this modification, and then we call our Fibonacci function, and then after that query the counter, then we get back the number of times we have referenced the variable n. And now we can play with changing Fibonacci to a C lambda. So this means it will capture the semantics at the time where the lambda was defined, right? So we will compile with respect to the current semantics of the tower. Okay, and this means when we set the counter to 0, we get the same result, right? But when we replace the variable evaluation with the old code, then the compiled version of Fibonacci still has the modified semantics, because that was the current one when the function was defined. Whereas if we recompile the Fibonacci function, then the counting behavior is removed again, right? So this is back to normal at this point. And in order to make this work, we had to make some restrictions compared to black. So where black essentially has simulates a separate CPU for every level of the tower, and it has separate environments. We only have separate environments, but we basically have one shared CPU that simulates the whole tower. And this allows us to do the compilation, because at every point we know what is the current semantics and with respect to what should we specialize. Okay, so this is the summary. So now we can collapse towers of interpreters. We have this lambda up-down calculus as a base language. We also showed how we can do the same thing based on LMS in a type-based way in Scala. And sort of based on the results we have, I think there's a pretty big design space where we can think about different ways of how should the APIs look like to expose compilation and so on, right? And I think there are also very interesting connections to be explored with respect to just-in-time compilers and de-optimization and re-optimization. Potential applications, yes, so I already talked in the beginning about towers in the wild. And then there's applications for reflection like security, properties, sandboxing, and so on. And that's all I have. Thank you very much. I'm happy to take questions. Yes, so the question is, since towers of interpreters introduce an exponential slowdown, how do we sort of keep that in check, right? And sort of now we're, instead of paying this exponential complexity for every bit of execution, we have some slowdown in the compilation, right? So since we're interpreting the compiler, and this goes through multiple levels, there might be some slowdown there, yes. So I think one thing you can do is kind of do a hybrid model, right, where you're sort of compiling a few stages, but then leave other stages in the tower in interpreted mode, right? So I think there's sort of tricks you can play by more fine-grained structures here. Another one, yes?
In your implementation of the definitional interpreter, how many parameters are passed and handled by a function? As a list of parameters at the same time, or as each parameter each time?
How many parameters does a function take in the definitional interpreter? Is that the question?
How many parameters are passed and handled by a function, and are they at the same time?
Okay, so in our definitional interpreters, so function only have single arguments, right? And each function also takes an extra argument, which is a self-reference that we use for recursion. And those functions, so since there's only one single argument for each function, this has to be at the same time, right? But we can do currying to support multiple arguments, and there we can have arguments that live at different stages, right? So we can have a function with mixed code arguments and normal arguments. I don't know if that answers the question, but I hope it gets close.